All right. So now we're going to get into some material today. Um, this is thermodynamics, new version of this software. Okay, so this is thermodynamics, and I'm going to start by um, just kind of giving a really broad picture of what we're talking about in this class. And then after I do that, we'll get into, the first topics in this class. But the main idea of thermodynamics is that we're exchanging um, thermal energy and mechanical energy. And there are going to be three main processes that we're going to talk about, three main cases. Um, there's going to be, and we'll talk about some other things too, but these are sort of the bulk of what we're trying to get to. And the other stuff we do is really just getting us into position to use these three things. The first one is a power cycle. And that is, we're going to use thermal energy to do mechanical work. I mean, all work is mechanical. If you remember work coming up in Physics 1, we'll talk about it a lot. And then the second one is the heat pump cycle. And the third one is the refrigeration cycle. And these two are really the same cycle. It's just that your goal is different for each one. And so what we're trying to do with the heat pump cycle and the refrigeration cycle is to use work to transfer thermal energy. And in both cases, it's sort of the same principle. In all three of these cases, it's sort of the same principle that we're going to use to do it. How do we do these? So first, if you heat a gas up, the gas expands. A piston rises, or it pushes out whatever the gas is contained in. It pushes out on the walls of the boundary. If it's a piston and cylinder, it pushes up on the piston. So let's just say a piston rises, and the result is that the gas does work on the surroundings. Um, and you can get the same effect backwards, with the other uh, direction of causation. If you force a piston down, the gas temperature increases.
And pressure?
Yeah, the pressure goes. We'll talk about the relations there. I'm just sort of trying to give the most basic, sort of intuitive idea of what we're talking about here. So it's these two sort of simple ideas. If you have imagine this piston being pretty well insulated, so not a lot of heat is going to be lost to the system. And if you force a piston down, the temperature of the gas goes up. How you would use that to create refrigeration isn't super obvious yet, obviously, clearly, but that is the mechanism that we're going to use. The types of calculations that we're going to do are we're going to deal with conservation of mass. Conservation of energy. And we'll talk about conservation of energy is the first law of thermodynamics. So that's how we'll refer to it. And then the third one is the total entropy of your system and your surroundings. So we're not talking about just the entropy inside a box or whatever. We're talking about all the entropy in the world. Total entropy can never decrease. Well, we have to define entropy and stuff like that, but and this is called the second law of thermodynamics. Oh well. And these things, all of them, we're going to do with kind of two approaches. The first one is called a closed system. And this means that over time, we're tracking the same molecules, the same material. And then the second approach that we're going to use is a control volume approach. And in that case, over time, we're tracking the same the same space, but material flows in and out of that space. Okay, so pretty much everything that we do in this class is going to relate to this summary of things. we're going to be dealing with the power cycle, heat pump cycle, and refrigeration cycle. And we're going to be doing it by looking at conservation of mass, conservation of energy, and the second law of thermodynamics that says entropy can't decrease. Okay, that's about it for the class, really. But obviously, there's a lot of little things we need to learn along the way. We will not really be dealing with vectors. Right at the start, I will a little bit, but for the most part, we're not going to be dealing with vectors. Is that text still big enough for you all to read? Okay. But there is an important sign convention thing that I want you to start getting used to now. So there's a very important sign convention that we're always going to use for the first law of thermodynamics. Oh, for criminy. And that is when we talk about heat transfer. This variable Q is always going to be positive for energy that's added to our chosen system. And when we talk about work, W is going to be positive for energy added to the surroundings by the system. That seems unnecessarily complicated when you're talking about conservation of energy. Why not just call everything additions to the system question?
In the refrigeration specifically, why would work stay positive?
Yeah, well, it won't. I mean, the Q and W can be positive or negative, but this is just like the sign convention. So if work is done on the system, that just means that our variable W has a negative value. Okay, like you'd have negative 30 kilojoules or whatever. Okay. And so the question is, why? Why would we do this? Well, it makes sense if you think of a power cycle. So let's think of a cylinder and a piston. This is like a cross-section picture. There's the cylinder. Here's the piston. This is the gas that's our system. and let's say you use a fire to heat up the gas. The result is that the piston rises, and you can use that rise in the piston to do work on the surroundings. And so what we have here is that heat is added to the gas. In other words, Q is positive. And then the result of adding heat to the gas is that work is done by the gas. And so that W is positive. So as you're starting out on these problems, we're going to do a lot of stuff early on where we're just dealing with this sign convention a lot, just trying to sort of, keep repeating it until it's just kind of your natural way of thinking. You can always remind yourself of what's going on intuitively by thinking of what happens in a power cycle. Okay, you add heat to the gas, and the result is that work is done by the gas on the surroundings. I'm going to give you a couple of problems after today on the assignment that just says stuff like, okay, so 50 kilojoules of work is done on the gas, and 150 kilojoules of heat is added to the gas. What's Q? What's W? Okay. And so you just have to think of like, am I taking the positive of this or the negative of this? Okay. I'll do one or two of those on Friday just to make sure you're thinking about it right. But anybody have any questions about that? All of that is sort of that's the overview, end overview. So now we're going to get into specific topics and just start working our way through this class. Okay, so the first thing we have to talk about is we have to talk about properties, states, and processes. A property is a measurement that represents the system at a single instant. So examples of properties are temperature, pressure, volume. Those are the three that we'll use the most. Entropy. Did you talk about enthalpy in chemistry at all? Did that ever come up? Enthalpy is a property. A state is all of the properties of a system at a given instant. So temperature is a property, but the state is defined by not just the temperature at that instant, but the temperature, the pressure, the enthalpy, the entropy, infinitely many things that define that instant. Okay. It turns out we're going to see that for almost any material, all the materials that we'll be dealing with, the most you ever need is two properties to totally define the state. So that's really nice. Like pretty much always, if you can come up with any two properties, you can find a way to determine any other property you want. And then a process is the transition between two states. Okay, so let's talk about these. Think about a question regarding these. So let's say that we're told that a gas has an initial pressure of 2.0 times 10 to the fifth pascals. I'm going to write this, by the way, in a shorthand. That's sort of how you enter it into a calculator. So I'll write this as 2.0 capital E 5 pascals. When you say this, don't say 2.0 times e to the 5, because that's a totally different thing. And then if you say that too often to chemistry instructors or whatever, then they come complain to me. So, but I'll just call that 2.0 E5. That's how you enter it into a calculator. And it has an initial temperature of 350 Kelvin and initial volume of 0.6 cubic meters. It's then compressed to a pressure of 3.0 times 10 to the fifth pascals, a temperature of 400 Kelvin, and a volume of 0.3 cubic meters. What are the properties, states, and what's the process? So okay, I'm going to use kind of a graphic or whatever, a way to visualize this that I'm going to use pretty often. So we can think of state one is the collection of all of these measurements that I gave you at that first instant. So that is going to be 2.0 times 10 to the fifth pascals. That's the pressure. A temperature of 350 Kelvin, a volume of 0.6 cubic meters. These three are the properties. And there are other properties that we just haven't measured, that make up this state. I mean, this state one has a certain entropy, it has a certain enthalpy, all the stuff like that. We just don't know what those are. So I'm going to go ... There's infinitely many other measurements you could take at that state.
Professor?
Yeah.
Is
Are pascals like nonlinear unit or
A what?
well the PA?
Uh-huh.
Okay.
That's pascals. That's just the that is just the SI unit for pressure. So that is newtons per meter squared.
Okay.
Yep.
Just to make sure I understand, like one of these individual measurements are like a property, while like all of them together is like the state.
Right. Exactly. Yep. So you could have. There's infinitely many states that have a pressure of 2 times 10 to the fifth pascals, but there's only one state that has, well, for a certain material that has a pressure of 2 times 10 to the fifth pascals and a temperature of 350 Kelvin. Then you can figure out like all these other properties based on that.
Sure.
And then state 2 would be that second set of measurements at that second instant. So that would be 3 times 10 to the fifth pascals, 400 Kelvin, 0.3 meters cubed, and all the things that go along with that. And in going from state 1 to state 2, that is the process. It's like a rainbow ink. By the way, notice that the first law of thermodynamics, conservation of energy, if you look at, well, I haven't told you what it is yet, I guess. So notice conservation of energy which is the first law, always deals with processes because you're talking about heat being added, work being added or removed. So you're talking about the transition from one instant to another one. So this always represents a process. And the first law of thermodynamics looks like this. The change in the energy from instant 1 to instant 2 in your system is equal to, so this is where that sign convention gets to be like a little bit of a nuisance. I mean, the first law of thermodynamics, conservation of energy, is an easy principle. It says the change in energy in the system, the only way you can change it is by having some amount of change in energy, and you have all these different ways energy can change. Well, Q, we're saying, is energy going into the system. You can also change the energy in your system by doing work on it or having it do work on the surroundings. But since our positive value of W would mean that work is being done by the system, energy is being lost by the system, this has to be minus W. I got to change some kind of setting here. Q minus W. Okay, so that's the first law of thermodynamics. I'm going to give you a couple of quick problems, like I said, to ask you to kind of wrap your head around this equation. If you have trouble figuring out what's going on, don't worry about it. The assignment isn't even due until after class, and I'll talk about it in class next time. So think if you can make sense out of it, and if not, we'll clear it up on Friday. Yep.
Is that still like I can't remember from like Chem 1, but is that the like standard change of enthalpy, like the work?
Yeah, that's the energy. And
change of energy, sorry.
yeah, but yes, that is a good question. Physicists use a different sign convention for that stuff. This is engineering first law of thermodynamics. And so, I mean, it's such a mess. Like different people use different, I would guess chemistry uses a different one, but I don't know.
It was like when we did some with work in the system, it was like Q plus, but then it was like negative work, so it looks
okay.
Similar.
Yeah, okay. Maybe it's the same, but it kind of has to do with what you, like in chemistry, for example, maybe the most common thing you deal with is that you create a chemical reaction and then heat leaves your system.
Yeah.
So then you might call Q heat that leaves your system to be positive. Exactly, exactly. But in this case, I mean, for us, since the most common thing that we're using heat for is to add heat to the gas to make it do mechanical work, we're just going to use this sign convention.
This looks very similar, yeah.
Yeah.
Thanks for clarifying.
Sure, yeah. Any other questions right now? Okay, so now let's talk about different types of properties. There are two types of properties. The first one is called extensive. And the second one is called intensive. We'll use these more often. So these will be more common for us. And the reason they're going to be more common for us is because you can look these up. But I have to make a distinction, define these two things so you know what you're looking at. So let's first define extensive properties. So the key thing about extensive properties is they're only defined if you choose an amount of material. And so you can think of it this way. If you partition a material into pieces. So let's say that this blob is all of our material, and let's say we break it up into 4 pieces. So let's say that this is region 1, region 2, region 3, and region 4. If capital P is an extensive property, and it is important that you're not talking about pressure here because, by the way, pressure is an intensive property, but P is for property. So if P is extensive, then the total P of the whole material is equal to P for region 1 plus P for region 2 plus P for region 3 plus P for region 4. Yes.
So like, is mass extensive?
Yes, exactly. Yep. Volume, mass, those are both extensive. So whoops. So let's say examples. Keep going. Volume, mass. Internal energy is an example. Entropy is an example. Usually, extensive properties are represented with capital letters, the variables. Sometimes it seems to do this little thing where it stops recognizing the pen. There we go. Usually extensive properties are represented by capital letters. So for example, volume is capital V, internal energy is U, capital U, entropy is capital S. But mass is the one that's different. This is an extensive property, but you represent it with a lowercase m. So keep that one in mind. So m is an exception. Then intensive properties. Are measured per unit. What unit that is can vary, though we're usually going to do it per mass. So we'll usually use per mass. Some examples of intensive properties. Are density. That's represented with the Greek letter rho. And that is an object's mass divided by its volume. The specific volume. So this is the intensive version of volume, and we'll represent that with a lowercase v. and that is equal to the volume per mass. And so notice this is important. If you know one of these, you know the other. They're just reciprocals of each other. The pressure, we write this as lowercase p, and this is force per area. In SI units, this is newtons per meter squared, which is called a Pascal. And then temperature, which is a capital T. And for this, we will usually want the absolute temperature. We'll talk a little bit more about temperature calculations on Friday. So we'll usually want this in Kelvin. So I said that the extensive properties almost always use capital letters. The intensive properties almost always use lowercase letters. The intensive properties usually use lowercase. Temperature is an exception. And one thing to notice, we're not going to do this too often, but you'll see it from time to time. So notice if you have a specific property well, you know, by specific I mean an intensive property. That's represented with an overbar. Like, for example, let's say volume with a bar over the top. That means per mole. Like I said, we're usually going to do these per mass, but if you ever see that overbar, try to remember that that means per mole. Anybody have any questions about that? Yes.
For temperature, can you represent that also as like something like then?
As what?
As like some property over per some property, like how that's mass over volume.
Let's see. You can do it somehow in terms of average. I don't remember how, but yes, you can somehow do it in terms of like an average kinetic energy per mass or something like that. I don't remember what it is, but it has to do with the like the mechanical meaning of temperature means like the molecules are moving faster.
Yeah.
You know, so yeah, but I can't give you what it is.
That's fair. But it's like to like being able to like make it like per unit is like what makes it intensive. Right?
Yeah, and also it just clearly is not extensive.
Yeah.
Because you can't, because the temperature, if you measure the temperature in this region, temperature in this region, the total temperature of the room isn't the sum of those.
Sure. Yeah.
the two variables under intensive, what are their names?
The two variables.
You said, but under your notice, yeah.
Oh yeah.
It's intensive, and then you had like two in the parentheses.
The first one just says for example. That's what the EG is, just example. And then this V over bar is the molar volume, the volume per mole.
Thanks.
Sure. Any other questions? Okay, let's stop there, and we'll talk about pressure, some pressure calculations on Friday, and we'll talk about some temperature calculations.